the next group, Andrew Brahms, Alan Duan, and Jacob Greene, and they speak about saturation of 0-1 matrices, and the mentor is Dr. Jesse Jennison from San Jose State University.
I'm Jacob Greene. We studied saturation of 0-1 matrices. So our objects of study are matrices whose entries are all 0 and 1, and we just think of these as patterns. So we'll write the zeros as empty space and the 1 entries as just dots, and we'll refer to them interchangeably using those terms, but this is what we mean. And the question that we're interested in asking about these matrices is, when do they contain each other? When does one pattern contain another? And so what we mean by pattern containment is that there's some submatrix of the larger pattern that corresponds to the smaller pattern. And corresponds meaning that you change some of the 1 entries to zeros, and then you get a copy of the smaller pattern. So here, we don't care if the submatrix doesn't have adjacent columns. Like here we take the first and last column. It doesn't matter. We're just looking for that arrangement of ones somewhere. So for another example here, both the patterns A and B are contained in the matrix M, which has, note that like the red dot in M doesn't mess with the fact that the pattern A is still contained in it. That's what we mean by changing ones to zeros. And so we can ask some questions like, how many ones can we have until we can't add any more ones before we introduce a forbidden pattern? So we have a particular pattern that we want to avoid, and then we want to build a matrix that does not contain that pattern, and whenever we added in an extra one, then it does contain that pattern. So such patterns would be called saturated. So an example, this matrix is saturating for this pattern P because anytime we add a 1 in one of those empty spaces there, then we would have 2 1s on the same diagonal, and then that would correspond to a copy of that pattern there. And so a question that we can ask is, how many 1s can we have in a saturating matrix? So for instance, for this 1x2 pattern, that's just 2 dots, what is the minimum number of 1s in an m by n p saturating matrix? So the minimum number of 1s that we can add to a matrix where if we added any more 1s, we would have to contain a copy of the pattern P. Does anyone know actually what this would be already? You might think about this. M, yeah, I heard M. It is, it's just M because there has to be exactly 1 1 in each row. And then whenever you introduce a second 1, you would introduce a copy of the pattern P. And so the notation here, we call this the saturation function, is the minimum number of 1s in an m by n matrix saturating for P. And what we just saw was that that saturation function is just equal to n. It's also been calculated for some other specific examples of matrices, like for instance the identity matrices. We know the specific value of the saturation function there. And there are also other concepts similar to saturation for other combinatorial structures like graphs and sequences, but we've just focused on matrices. But so the first tool that we have to study saturation is a weaker condition, so semi-saturation. We say a matrix is semi-saturated if whenever we add in a new 1 entry, then we add a new copy of the pattern. And so we've removed the requirement that it doesn't contain the pattern originally. And this is useful because the semi-saturation function always provides a lower bound for the saturation function, because this is a strictly weaker condition.
New pattern could intersect the old ones.
Yes, yes. So an idea for this, for that pattern that we saw earlier in the first example of saturation, this matrix is semi-saturating, because if we added a 1 on the top row or along that column, we would have that 1 plus the 1 in the bottom right, and then another 1, that 1 together with this 1. Either way, we would introduce a new copy of the pattern, but we already have a copy of the pattern, so this is just semi-saturating. But so, in general, it's very difficult to determine the exact value of the saturation function. So we're only interested in the growth rate of the saturation function, and there's actually a very nice characterization for this. For any pattern, as n goes to infinity, the saturation function for an n by n matrix with P is either linear in n or it is bounded. So there will be some fixed number of ones that we can introduce to any size matrix that will already make it saturated. And the other statement of this, sometimes we're interested in square matrices, but sometimes we're interested in fixing one dimension and letting the other one go to infinity. And often the case of fixing one dimension is simpler. But in both cases, we have this interesting dichotomy. And so the question that we're asking is, for which patterns are we going to have this saturation function is linear, and for which patterns are we going to have that it's bounded? So, Alan.
Thank you. And so to answer this question, there are a few simple conditions for a pattern P to have a linear saturation function. And so, for example, if P has at least two one entries in every row or every column, then it has a linear saturation function. Or if it has no one entries in the first or last row or column, then it also has a linear saturation function. And this is because the semi-saturation function will be linear as well. And since, as Jacob discussed earlier, semi-saturation is a lower bound for saturation, so linear semi-saturation leads to linear saturation. And the next condition is called decomposability. And so we say that P is decomposable if it's of the block matrix form, like with A and B and zeros in the corner. And so every decomposable matrix has to have a linear saturation function. And this condition is pretty important because on one hand it classifies a decent amount of patterns, but also it's useful when looking at permutation patterns as well. And so our mentor, Jesse Jensen, he proved that almost all permutation matrices have bounded saturation functions. And he did this by showing that multiple infinite families of permutation matrices all had bounded sat functions. And then through a calculation, he showed that this constitutes like almost all of them. And later, Berenson proved an exact classification of which permutation matrices have a bounded stat function. And it turns out that it has a bounded stat function if and only if it's indecomposable. And notice that I think the only if part of this theorem is just the contrapositive of the decomposability condition from the previous slide. So what Berenson did was prove the converse of that, which turned out to be much harder. And so to prove this, we need some tools. And so we define an expandable row to be a row in a matrix that consists of all zeros. And if you change any zero in the row to a 1, you get a new copy of your pattern. And we define a similar thing for columns. So for example, if we have this matrix M here, and the pattern P is just 3 ones in a row, then the second column is just expandable with respect to P because changing any 0 in the middle column to a 1 would just complete that row, which is just P. And so using this definition, we can define a witness for a pattern P to be a matrix M such that M doesn't contain P and it has both an expandable row and an expandable column. And so we can also define horizontal and vertical witnesses, which are just P-free matrices that have just an expandable row or just an expandable column. And witnesses are useful because a pattern P has a bounded stat function if and only if there exists a witness. And so what this means in practice is that if we want to find if the stat function is linear or bounded, we either can construct a witness which would show that there's a constant stat function, or we can prove that such a witness can't exist. And also a similar thing exists for horizontal and vertical witnesses, and that just shows boundedness in the case of fixing one dimension. And so for example, we claim that this permutation matrix P has a bounded saturation function, and the witness matrix that corresponds to this is this matrix W, and one can manually see that the dotted row and the dotted column are both expandable, and also that W does not contain P. And so because W is a witness for P, then we know that P has a bounded saturation function.
Now we can start talking about some of our results. And one of the big picture questions, as Jacob said, that we looked at is what happens when we fix one dimension? And more specifically, when can we go from there existing a horizontal witness and a vertical witness for a pattern P to there existing a matrix that can serve as both, which would then imply what you see on the screen, that P has a bounded saturation function. Now there has been some prior work done on this subject. Berenson showed that for all patterns P that satisfy this condition on the last row and the last column, we necessarily have that the relation holds. So if you have a pattern P that only has one row, one in its last row and one in its last column subject to rotation, then all you have to do to show that P has a bounded saturation function is to construct a horizontal witness and a vertical witness for P. Now this is a pretty useful result, as evidenced by the fact that we used it a lot, but it's also pretty narrow in its scope because this condition on P is pretty strict. So the natural question is, how do we generalize this to more patterns P? And it turns out this is a pretty difficult question, in part because in the general case it's not actually true, as we showed, because the natural generalization, which would say that in general, if you have a pattern P that has a horizontal and vertical witness, then it has to have a bounded saturation function. We were able to prove a counterexample to this in this pattern P, which has a horizontal witness and a vertical witness as we constructed, but because it doesn't have any ones that are alone in its row and column, the semi-saturation gives that it has to have a linear saturation function. So what this means is that for this pattern P, if you fix one of the dimensions, the horizontal or the vertical dimension, and allow the other one to vary, it has a bounded saturation function. But if you allow both of the dimensions to vary, then it has a linear saturation function. Now this is a pretty counterintuitive result, and it's also a pretty annoying result if what we're trying to do is generalize the theorem of Berenson. So what we actually have to do is we had to place some explicit conditions on the witnesses for P. So this is our generalization, and it's quite a lot on the slide, but the main two takeaways here is that this condition on P applies to, to borrow Dr. Jennison's terminology, this applies to almost all matrices P as P grows large. And also this condition on the witnesses is both necessary and sufficient. And the reason that this doesn't cause an immediate contradiction is that in Berenson's result, this is actually implied by the condition that we have on P. So the two obvious generalizations of this theorem, the further questions would be, how do we generalize this to patterns that do not satisfy this form? And for what patterns, other than the ones defined by Berenson, can we imply that P has this condition that for every witness there has to have a one that is along both its row and column corresponded to. So these are both open questions and areas for further research. We have a few more results on what happens when you fix one dimension. For example, for the saturation function, or for the semi-saturation function, we were able to classify all matrices according to whether or not their semi-saturation function is bounded. We also have an explicit upper bound for what the saturation function is in this fixing one dimension case when we're given that the saturation function is indeed bounded. Another thing that we looked at was what happens when you add empty rows and columns internally into a matrix. Now, as shown on a previous slide, if P has an empty row or column as its first or last row or column, then we know that it has to have a linear saturation function. But what happens when we add columns and rows internally is still the subject of research. So the two results that we have over here is that when we fix one dimension, then if we fix the number of rows, then adding an internal empty column doesn't change the saturation function from bounded to linear. And also, if we have a permutation matrix, then adding an internal empty row or column doesn't change the saturation function from bounded to linear, which is very useful because, as we already seen, we already have a classification of all of the permutation matrices. So finally, we proved the classifications for these patterns on the slide, which completes the classification for all 4x4 previously unresolved patterns. For Q2 and Q3, we were able to create infinite families that generalize those two results. And so we would like to thank our mentor, Dr. Jennison, as well as the MIT PRIMES organizers and all of you for your attention in this talk.
Questions? Okay, Jacob.
You were talking about characterizing when it's constant and mostly constant and when it's prolinearly. Do you have results about what the growth will be as a function of P, so the forbidden thing? So you have a big O1 which will depend on your P that you're forbidding. I was just wondering if you have more precise things.
Oh, okay. So just to clarify, you're talking about when so for these infinite classes of matrices, or?
So you have a few different results. Sometimes you know it's linear, sometimes you know it's constant. And say it's constant, do you know how big that constant can be or will be as a function of P?
Yeah, so for the case where we have over here, this defines an explicit upper bound for when we have that one of the dimensions is fixed.
Mm-hmm. So this gives an upper bound. Just wondering if you have like you have a tight bound for this.
Yeah, so I think in Berenson's paper on permutation matrices, he proved that the saturation function is like at most 9 times the dimension of P squared. So like 9k squared if P is k by k. And basically the bound just comes from finding like a small enough witness matrix. And so the size of the witness will like kind of determine your bound in terms of P.
Are there lower bound examples like that in the same ballpark?
I'm not sure.
We don't really know any lower bounds.
Okay, other questions in the back? Speak up, please.
Your definition of submatrix will allow to take non-consecutive rows and columns. I was wondering what if we restricted to only allowing consecutive rows and columns? How would the results change?
We don't know. We've really thought about it just with our definition of pattern containment. We can imagine that if we certainly if you restrict it to requiring consecutive rows and columns, then the saturation function would never be bounded, because you would not be able to have large empty areas. So it would probably have more complicated growth rates.
Other questions? Leo, please.
Okay, yeah, so there's been a few papers on like higher dimension, like multi-dimensional matrices, and I don't remember the exact results on the top of my head, but I think, do you remember?
Yeah, so if I remember right, we haven't established a nice result like the two-dimensional dichotomy. We have established that it's never like strictly more than bounded and sublinear, but then there's still the question of where it is between linear and theta of n to the d, where d is the dimension. And I believe that for the semi-saturation function, they've actually shown that it's theta of n to the k for some k between 0 and d. But a big open question there would still be, for the saturation function, is that also true?
So is it always
It's always bounded by theta of n to the d, just because there are n to the d entries in n matrix. So.
Other questions?
Several of the results are for like permutation matrices P. I was wondering, like, could it be generalized to like circular matrices, or do your proofs like significantly rely on the structure of like permutation matrices?
Circular, exactly, circular.
Oh,
Circular.
like the rows are like shifted, or like just like one time.
I think that would have like more than that would have like at least 2 1 entries in every row, right? So that would be from the previous slides. It'd have to have a linear saturation function.
Okay, thank you.
Other questions? Okay, let us think. Now we have to have picture.